appreciate with the people with this conference, and of course it's not just in my honor, it's in honor of our Charlotte Scott Research Center for Algebra, 10 years in Lincoln. And because of this kind of historic occasion, I will show you the photograph of the previous conference, which happened 8 years ago in Lincoln. It was the first mathematical conference ever in Lincoln. And as we see, many of today's participants are here in the sun in Lincoln in 2016. So, well, okay, so let me just say it was really a great time in Lincoln, building up the school, the mathematics programs, and research, of course. And our research is quite strong. We have a very good and very strong group, and with many connections all over the world, on all continents and so on. And yeah. Anyway, let me now pass to the scientific results, the research talk. And the results in this talk are joint work with Kristina Chiari, Robert Guralnik, and Pavel Shumetsky. So the title of the talk is Local Global Rank Properties of Commutators. And therefore, I have to begin with definitions of rank. What is rank in this talk? Rank is here the so-called Prüfer rank, which means that a group has rank at most R if every subgroup can be generated by R elements. Every subgroup of G can be generated by R elements. And, well, restricting the rank, bounds for the rank is a very good thing in a sense. It's quite a desirable property. There are just a selection of nice consequences of having a bound for the rank. For example, if we have a finite P group of given rank R, then there is a powerful subgroup of index bounded in terms of P and R. And of course, powerful P groups is a very nice object with very nice properties, which makes it easier to study. And in a sense, the other way around, if we have a powerful P group of given rank, for powerful P group, the rank is simply the number of generators. So these are really nice type of P groups. There are consequences of the theory of powerful groups, like profinite group of finite rank is virtually soluble, a reasonably finite group of finite rank is virtually locally soluble, and so on. Another consequences of a bound for the rank of a group is the bound for the ranks of the elementary abelian sections. And these sections can be regarded as vector spaces or finite fields on which group acts by conjugation, and therefore results on linear groups can be applied. For example, if we have a given dimension, then theorem of Zassenhaus says that a soluble group has certain properties of given dimension has very nice properties. And therefore, a consequence is that if we have a finite soluble group of given rank R, then it will have R-bounded fitting height. And so on. There are many other consequences. This is just a selection of examples. Local global generating properties. Here is this slide is about an example about the order of the group, which is a kind of just an elementary example, which simply shows what it is about. So in general, if we have a small number of generators, it does not mean that the group is so small, of course. The group can be very big, even with 2 generators. But for some special set of generators, we have this nice property. If we have just given number, finite number m of commutators in a group, then the derived subgroup is finite and has bounded order. So commutators are simply generators of the derived subgroup, and in this case, number of generators implies bound for the order. And well, this is a well-known exercise or example, but I give you a proof just as a kind of entertainment, as an elementary exercise for students, maybe using Schur's theorem. So if we have this many commutators, we can simply list them all. Let these be all m commutators in the group. And if we take the centralizer of any element, actually any element of the group will have centralizer of index at most m, because cosets of centralizers will be corresponding to different commutators with this element. And therefore, the index of the centralizer of every of these elements is at most m. And if you want to bound something about the derived subgroup, it is generated by these commutators. And for this reason, we can simply assume that the group is generated by these elements. Now we simply take the intersection of all these centralizers. It will be just 2m subgroups, each of index at most m. So the intersection will be a subgroup of m bounded index. And this will centralize each of the generators, and therefore will be in the center of the group. If you centralize all generators, then you centralize all elements. So now we have a central subgroup of m-bounded index, and we only need to apply Schur's theorem. This is Schur's theorem, that if portion by the center has order, given order, then the derived subgroup has bounded order. So with this kind of example of local global property, so we have a local property, meaning that we have these many generators, but now we have a global property, the order of the subgroup generated by these elements is bounded. And this, we can now state one of the examples, one of the theorems, actually one of the consequences of our theorems about rank. So again, in general, small number of generators doesn't mean we have a small rank, but one of our consequences of our results is the following. Suppose we have for certain positive integer r, we have this local property. Well, instead of finite number of generators, we simply say that any subgroup generated by a subset of commutators can be generated by r elements. And the conclusion is that the derived subgroup has r-bounded rank. So actually, we prove somewhat stronger results, which will be stated below, but here simply to make a parallel to the previous example. So here, this local global property means that we have local condition that any subset of the generating set can be R subgroup generated by this subset can be R generated. But the conclusion is global, that every subgroup of this derived subgroup can be generated by a bounded number of elements. To state our results in more detail, we need more notation, and here is a notation for the commutator set for a certain subgroup, or even a subset of a group G. We use this notation IG of S, the set of all commutators, where S is an element of S and G an arbitrary element of G. So then, of course, the commutator subgroup GS is simply generated by this set of commutators. And of course, as usual, normally this is not the set of commutators. The subgroup is usually much bigger. And Well, with this notation, I can again give an example of local global property with respect to order. Again, this is an elementary example. Suppose we have some subgroup S and this set of commutators is finite. So for order, we have this set of commutators finite of cardinality M. Then again, just like in the first example, this commutator subgroup has M-bounded order. Well, the proof is again elementary, again based on Schur's theorem, and maybe I quickly list it here. So again, we list all these commutators because we have a finite set, we can list them all. Again, the index over is centralized of elements of S have finite index, and in each we can find a normal subgroup. This normal subgroup will centralize the commutator subgroup G and Si, and so this means that this commutator subgroup GSI has set of M-bounded index. Again, we apply Schur's theorem, obtain derived subgroup of bounded order, and in the next step, we consider the abelian quotient by the derived subgroup, and for the abelian quotient, the subgroup actually consists of images of commutators. And therefore, again, it has order at most n by hypothesis. And as a result, the whole subgroup GSI has M-bounded order. It only remains to note that this commutator subgroup GS is the product of these GSIs. The number is M, each has M-bounded order, therefore the order of GS is M-bound. So this is again just an elementary example, but now one of our main results in this talk is this theorem 1, which is a kind of rank analog of the same example on the previous slide. Here we deal with the CLFP subgroup of a finite group G, and we assume that the group finite group G is P-soluble. So P is a prime, R is a positive integer, and P is a CLFP subgroup. Suppose this local condition holds, any subgroup generated by a subset of these commutators can be generated by R elements, then the whole commutator subgroup GP has R-bounded rank. So again, this is this type of local global property. R generation by subsets of this generating set implies bounded generation of all subgroups of the commutator subgroup GP. Well, here we have this condition P-soluble, and in fact, this is essential. This condition of P-solubility cannot be dropped. There are examples, a series of finite groups which have a CLFP subgroup such that any subgroup generated by a subset of these commutators can be generated actually by 3 elements even, but the rank of the commutator subgroup is unbound. So this P-solubility condition in the theorem cannot be dropped. Well, the remark here is that in fact, these examples are some SL2 Qs, certain prime powers Q. And moreover, there is a hope, and this is a kind of work in progress, that we could prove that these SLQs are the only exceptions. And if we manage to prove this, then the theorem could be extended to all finite groups without P-solubility condition, but of course with additional dependence on the ranks of these abstractions to the theorem. Well, another result which applies to arbitrary finite groups without P-solubility condition, but of course it cannot be the same theorem 1. Here we impose an additional local condition. So part A is the same condition as in theorem 1. Any subgroup generated by the subset of these commutators with elements of C of P subgroup can be generated by R elements. And in addition, for any commutator in this set, if you consider another iteration of this commutators, again, any subgroup generated by such a subset can be generated by R elements. With this additional local condition, we again obtain this global conclusion that the commutator subgroup GP has R-bounded rank. Well, so this additional condition is essential because of those examples, so it cannot be dropped to deal with those exceptions. One more theorem is again for arbitrary finite groups, but here the condition, the hypothesis is for all T of P subgroups, overall primes dividing P. If this subset, every time any subset generated by a subset of these commutators can be generated by R elements, and this holds for every P dividing the order of the group, then the whole derived subgroup of G has R-bounded rank. Well, this has already been stated as a corollary at the beginning of the talk, but here it's a kind of stronger result because the condition is not imposed on all commutators, but only on commutators with elements of C-log subgroups. These theorems, well, the important tool in the proofs is actually a result about automorphisms. And this result about automorphisms is of independent interest, and this is our theorem 4. So here we have a finite group, arbitrary finite group, admitting a group of coprime automorphisms A. And the condition is that for a certain positive integer R, any subgroup generated by a subset of these commutators can be generated by R elements. Then the commutator subgroup GA has R-bounded rank. Well, of course, here we regard A and G as subgroups of the natural semidirect product. So these commutators are regarded in this way. So commutator of G and automorphism A is simply the product G inverse and the image of G under A. And this is the same as commutators in the semidirect product. Well, this theorem grown out of a recent paper by Acharya, Guralnik, and Shumyatsky. And in particular, one of the results in that paper was that, which is worth mentioning here because it's also used in the proof, that if you have a cyclic group of automorphisms, coprime automorphisms, and if every commutator has odd order, then the subgroup GA, the commutator subgroup, must also have odd order. It's another type of local global property for these commutators. So there will be some time for me to discuss the proof, make it a scheme of proof of theorem 4. This is what I will be doing. But before that, well, I just mentioned that the proof uses Rivot-Schiemann theorem of power groups and also results in representation theory of whole Higman type, and quite a lot more of technique. The proof is kind of long and technical. The number of lemmas is more than 20 in the proof, so it's far from easy, this result. And maybe also make these remarks on duality, kind of duality photomorphisms, because one of the very usual ways of studying automorphisms of finite groups is imposing smallness conditions on the fixed point subgroup, same as the centralizer in symmetric product. And there are classical work of Thompson and Higman on automorphisms with small number of fixed points, and a lot of results were proved in this direction. And also in this study of smallness conditions of the fixed points, this can also be generalized to the rank. As we saw on previous slides, some results on order can be extended to rank. In particular, myself and Samazrov, we proved results on finite groups with a group of automorphisms such that the fixed point subgroup has small rank. For example, if A is cyclic of prime order and there is rank R of the fixed point subgroup, in addition, you have to assume it's coprime if G is insoluble. Then, in fact, there are normal subgroups such that G over H has bounded rank and N has bounded rank. But the middle bit, the quotient H over N, is nilpotent of class bounded in terms of P only. So this is a kind of rank analog of Higman's theorem or maybe Thompson theorem. And in this result, both sections G over H and N are important. But anyway, in theorem 4, we kind of consider a dual condition, because this set of commutators can be regarded as a kind of dual to the set of fixed points, to the centralized. For example, if we simply consider a single automorphism alpha, then we always have this equation. The number of commutators with alpha is simply the index of the centralizer, of the fixed point subgroup. So in this sense, theorem 4 and the previous theorems by Chiari, Duranik, and Shumyatsky, this represents the dual direction where these conditions, smallness conditions, are imposed on the set of commutators, and then these conditions strongly influence the structure of the derived of the commutator subgroup GA. Okay, but now I also mention very recent results on commutators with elements of Carter subgroups. And first, the definition, just remind you of the definition. A Carter subgroup of a finite group is simply an nilpotent self-normalizing subgroup. Self-normalizing simply means its normalizer coincides with this subgroup. One way of when Carter subgroups appear is actually by way of automorphisms. If you have an nilpotent group of automorphisms A, such that the fixed point subgroup is trivial, if this is the case, then A is a Carter subgroup. Then to the Carter subgroup of the semi-direct product G and A. But in general, Carter subgroups were proved to exist in every finite soluble group. This is actually Carter's theorem. He proved that every finite soluble group has Carter subgroups. All of them are conjugate. And the image of a Carter subgroup in a quotient is again the Carter subgroup of a Carter subgroup of this quotient. So these Carter subgroups play quite a significant role in theory of finite soluble groups, and their generalizations are often used widely in the theory of formations, for example. But apart from soluble groups, in arbitrary finite groups, there may not be any Carter subgroups. But some finite groups, even insoluble groups, still have Carter subgroups. And it was some recent work, relatively recent, of course, maybe now 15 years ago, by Evgeny. He used classification of finite simple groups to prove the same theorem as Carter's theorem for any finite group that has a Carter subgroup. It simply means that if a finite group has a Carter subgroup, then all Carter subgroups will be conjugate, and in the quotients, in the homomorphic images, the images will be Carter subgroups of the images. And he also determined, he actually completely classified Carter subgroups in all almost simple groups. He determined when they exist and gave full descriptions. And Carter subgroups often behave like coprime groups of automorphisms. They have this kind of influence on a group. Here is a good example. First Thomson proved that if we have a coprime group of automorphisms A acting on a finite soluble group G, then the fitting height of G is bounded in terms of composition length of A and the fitting height of the fixed point subgroup. And he conjectured that the same should be true for a Carter subgroup. And they solved this problem. He obtained a bound for the fitting height of a soluble group in terms of the composition length of a Carter subgroup. Okay, so our theorem for commutators and Carter subgroups says the following. If we have, first for soluble groups, if we have a finite soluble group G and C is the Carter subgroup such that any subgroup generated by a subset of commutators like this with elements of Carter subgroup, if any such subgroup can be generated by R elements, then the commutator subgroup GC, which is actually the same as the derived subgroup of G, has R-bounded rank. So it's a similar kind of local global result about subgroups generated by commutators. Well, again, this theorem does not hold without the assumption of solubility. Again, a series of examples were produced, and again, it seems that such examples exist only for a small class of almost simple groups. So it should be really possible to obtain a bound for the rank of derived subgroup in terms of R and the rank of these abstractions without assuming that they will be soluble, but then introducing the ranks of these abstractions in the conclusion. So this is really some work in progress. It's not really written down completely yet, that indeed such a theorem seems to be possible, that if we have a finite group containing a Carter subgroup, so this is assumed that the group contains a Carter subgroup, and any subgroup generated by this subset of commutators can be generated by elements, and then the rank of the derived subgroup is bounded in terms of R and the maximum rank of composition factors isomorphic to this specific PSL2 fields. So these are the results, and now in the remaining time, just a few words about the proofs, some scheme of the proof, some bits of the proofs of, and I will focus on theorem 4, because theorem 4 is really important in the proofs of all these theorems. All proofs depend on the classification of finite simple groups as well, except the theorem 5, which is on soluble groups. And so I will say a few words about the proof of theorem 4. In in theorem 4, we can, of course, assume that G is the commutator subgroup GA. We have coprime automorphisms A, group of coprime automorphisms, and any subgroup generated by those commutators is R-generated. And the goal, the aim here is to prove that G, the group, has R-bounded rank. So first, this is proved for the case when G is nilpotent. Then we consider so-called semi-simple finite groups, which are simply direct products of non-abelian simple groups. Again, prove this result. Then we use whole-Higman type theorems to bound the order, the exponent rather, of the automorphisms induced on the quotient by the generalized fitting subgroup. This is combined with a result of the previous paper of Chiari, Kuranik, and Shumyatsky, and then the result follows for the case of cyclic A. Then a certain key proposition is proved that G can be generated by R-bounded many orbits of elements of these commutators, and then all of the above is combined to reduce the case to the case where A is a P group and the of R-bounded derived length, and the proof is finished by induction on this derived length. So, well, this is not really very informative what is written on this slide. So let me show a bit more. When G is nilpotent, of course, it is sufficient to consider only the case of finite P group. So we can assume that G is a finite P group such that it's equal to this commutator subgroup GA, and then theory of powerful groups is employed. But I think this is a bit too technical for this talk, so I kind of skip these arguments, well, anybody really interested can, of course, find our paper in our archive and see these arguments involving powerful P groups, where a powerful subgroup is constructed, and which, of course, then makes it easy to obtain the bound for the rank of G. Another step in the proof is considering semi-simple groups, and here again some bit of proof can be shown. So first, when G itself is a simple group, the classification is used to show the rank must be R-bound under that local condition. And for example, when we have a semi-simple group, which is direct product of simple group, suppose these factors are transitively permuted by our automorphism group A. So now we can easily show that the number of factors must be bounded by R plus 1. Why is this? Because we can simply take an involution T in the first factor. Then we can take these commutators. These are actually commutators. T inverse times T to the A with A in A. When we use this transitive action, we can take T to the A in all other factors, and therefore some of these having T to the A in different factors sorry, will give us an elementary abelian subgroup of rank m-1. And these are elements in our set of commutators. By our hypothesis, it must be of rank at most R. And therefore, we obtain this bound for M. As a result, the whole semi-simple case has is settled by the bound for the rank is obtained in the case of this transitive action. And also, well, of course, I'm skipping many of these details, in particular, the theorem from Chiari-Guralnik-Shmelsky paper is used that there must be some elements such that these commutators have even order. Now I can show you some bit of a proof for application of Hall-Higman type result. And this is done in this context. We have this group G equal GA for coprime automorphisms with our condition, and we wish to show that the exponent of the automorphism induced on the quotient by the generalized fitting subgroup is the exponent is R-bound. For this, we can of course simply take only need to show that elements of prime power order have bounded order acting on this quotient. And because of the previous step for semi-simple groups, it's really sufficient to consider kind of a seal of R subgroup of this fitting subgroup, and this symmetric product R and times A acts on elementary abelian Q subgroup of f of G. So this is a kind of situation to which everything boils down, and this is known as a non-modular Hall-Higman type situation. We have a symmetric product of a R group R times this cyclic group of order p to the m, and this symmetric product acts faithfully by linear transformations on a certain section of f of G, which is a Q group, elementary abelian Q group, regarded as a vector space over field of Q elements. And because of this Hall-Higman type situation, we could apply Hall-Higman type results. There are classical results of Date, Schult, and Gross, but only if alpha also acted faithfully on R. If we knew that alpha acted faithfully on R, then we would have this nice conclusion. The minimum polynomial of alpha on V would have degree at least p to the m minus p to the m minus 1, and this would work very well for the rank. I will show you a bit later why. But in this situation, in our situation, we cannot assume faithful action of alpha on R. We have faithful action of the symmetric product on V, yes, but we don't have faithful action of alpha on R and G. Well, fortunately, this is our situation. There was a recent work of myself and late Wolfgang Moens, where we indeed simply considered this situation, exactly this situation, and proved that just like in those classical results of Date, Schult, and Gross, the minimum polynomial is indeed at least of degree at least p to the m minus p to the m minus 1. The proof in this paper of myself and Moens is really similar to the classical proofs of non-modular Hall-Higman type situations, but it's really it's a small but new variation of this Hall-Higman theme. Well, as a result, we know that this degree of the minimum polynomial is simply the dimension of the span of the orbit of some element of V under alpha. And when we take these elements minus V plus V to the alpha, these are commutators of V and alpha. So they belong to our set of commutators, and therefore, this dimension is the rank. When we take minus V plus alpha, dimension can only be by 1 less. So we obtain this inequality. P to the m minus p to the m minus 1 is minus 1 is less than or equal to r. And this actually implies that p to the n is r bar. That's right. Well, and then of course this all is combined to finish the proof of theorem 4. Theorem 4 in turn is used in, and some of its lemmas is heavily used in the proofs of all other theorems. Anyway, this is where I should stop. Thank you.